So I'm here again at the University of Copenhagen in a park actually just adjacent to the venue that we've been listening to a lot of great papers with Eddie Schwieterman, who is an astrobiologist at the University of California, Riverside, who's come all the way here to give a paper entitled, what is it, Eddie?
Challenges for advanced life in the habitable zone, implications for the search for life in the universe.
And so what is the habitable zone for the uninitiated?
Right. So the habitable zone is this conceptual range of distances around a star in which you could have stable liquid water on the surface if given the right atmospheric composition. And of course, the extent of this distance depends on how bright your star is. If you're too close, the oceans boil away. If you're too far out, the oceans freeze. But within this narrow range, you actually require a greenhouse effect in the atmosphere in order to maintain surface liquid water. And the most common greenhouse gas invoked is carbon dioxide. On Earth today, carbon dioxide is relatively low, 400 parts per million, although increasing due to human activity. But for the vast majority of the habitable zone, substantially more CO2 is required, up to several bars or several times the mass of Earth's atmosphere at the outer edge. And such a large amount of CO2 would have deleterious impacts on large complex organisms like humans or animals, or their analogs on exoplanets. And so the idea, therefore, is that the habitable zone for microbial life is much larger than the habitable zone where we could imagine Earth-like biospheres with animals and possibly intelligent beings, which would be much more restricted. And this might have consequences for, how often we'd anticipate a civilization arising in our galaxy. So I'm going to talk about that, and I'm also going to talk about how we'd search for those civilizations if they do exist through what are called technosignatures.
Right.
Technosignatures are remote indicators of technology, either from an active civilization or something that was left behind. And specifically, there are things called atmospheric technosignatures. These would be artificial gases that exist in the atmosphere that we would otherwise not expect from abiotic processes or from processes from simple life. And so we can analyze the spectrum of the planet, breaking apart its component wavelengths, and then search for the unique signatures created by those gases.
But the thesis of your paper automatically assumes that if the habitable zone is wider for microbial organisms are going to be more ubiquitous than intelligent life, which may be fewer and far between. Is that right?
That's right, and I suspect that's true, but the only way that we'll know that for sure is by looking. What is the propensity to find biosignatures or indicators of relatively simple life? Photosynthetic life makes oxygen, for example, in the atmosphere. Might search for that, versus these more advanced forms of life that may create technology. There are those who think that intelligent life may be more common. Intelligent life has the advantage of being able to move from planet to planet. And so we can test this observationally, and no matter what, we should always be willing to be wrong.
But how has our own habitable zone here in our solar system evolved over time? Because it's changed quite a bit, hasn't it?
That's actually a great question. So the sun has gotten brighter with time. It was about 70% of the luminosity 4 billion years ago, of its current luminosity 4 billion years ago. And therefore, you can think of it as the Earth has actually moved in the habitable zone from somewhere in the middle to somewhere basically close to the inner edge. And consequently, this is completely consistent with the CO2 story, because we know from our geochemical record and our climate record that likely the CO2 in the atmosphere has gone from a much higher concentration to a much lower concentration. This is over billions of years due to complex biogeochemical processes that have weathered that CO2 and deposited it in the interior of the planet.
And even though Mars, for instance, which is a little bit further out in our own habitable zone, it's on the outer edge of the habitable zone, it was stripped of its atmosphere and now is largely CO2, but it only has less than a 1% atmosphere, right?
Right, so there's 6 millibars of CO2 on Mars. We suspect that Mars might have had liquid water for at least some of the time, very early in its history. Due to morphological features that appear to be like river deltas, things like that on the surface of Mars. And so folks have investigated what kind of atmosphere would have been required for Mars to have those habitable conditions very early on. And it would require a lot of CO2, in addition possibly to other greenhouse gases and their contributions. And that amount would be several, few to several bars of CO2.
But we know that, since our own habitable zone changed as our star evolved, are we lucky to be here, as intelligent beings talking about all this? Is it a fluke? Or would you think that if a planet evolves microbial life, it could potentially evolve intelligent life?
Well, I would say because of the evolution of the habitable zone to the brightening of the sun, the Earth is not just in a special place, it's in a special time. When we get enough radiation from the sun to be able to maintain a clement, habitable climate with relatively low levels of CO2. And as organisms that breathe oxygen and exhale CO2, we have the advantage and privilege, and I don't think it's a coincidence, that we live in a world where we have a lot of oxygen and very little CO2.
So if you're looking at exosystems, exo-Earths around sun-like stars, and we're like 4.567 billion years old, our planet and our solar system, pretty much, roughly. Halfway through the main sequence life of our star, while it will continue burning hydrogen before it goes off the quote-unquote hydrogen burning main sequence. So when you're looking for technosignatures, when you're looking for intelligent life particularly, would you be better served to look for stars, take the ages of solar type stars in their middle age stars, so that the exo-Earths that might circle that star have had time to evolve not only intelligent life, but a habitable zone which is suitable for life?
Well, in part, the relative importance of the habitable zone depends on where the planet started out, right? So did it start
and the
out,
distance from the star?
And so the distance from the
but
star
let's
in
assume,
the beginning and the luminosity
let's
of the
assume
star.
like one AU from a G-type star like our own. The age would play a factor.
Exactly, yes. So we want to have enough time for the biosphere to evolve, for organisms to develop, for these evolutionary transitions to happen. But those evolutionary transitions are likely coupled to the biogeochemical evolution of the planet, which is itself partly impacted by the evolution of the star.
So thanks so much, Eddie, for and anyway, and if you had to walk away, what is the bottom line, the takeaway from all of this?
Well, the bottom line is that the word habitability can be ambiguous, that the area around the star in which we might find biospheres that have microbial systems that create atmospheric biosignatures might be much larger than the relatively narrow range in which we might expect more complex biospheres that include intelligent life.
Okay, well, Eddie, thanks so much for your time. Appreciate your talking to us.
Thank you.